So, good morning, good afternoon, and good evening. Hope you're all doing well. I am Mariam Shref, a senior petroleum engineering student at the Lebanese American University, and I'll be moderating today's session. So, welcome to the last session of our online course, Artificial Lift Technology Methods, which has been presented by a distinguished, outstanding speaker, Dr. Mohamed Ghareeb. So I will reintroduce Dr. Ghareeb. Dr. Ghareeb holds a PhD in petroleum engineering with emphasis in artificial lift and production and operation. He's a lecturer at Future University in Egypt. Dr. Ghareeb is a technical and business professional with over 34 years of experience in oil and gas business, operations management, engineering, sales, and teaching. To highlight, he presided several positions at various international service and operation companies, including being a vice president, director, and finally a general manager. Over the past years, he played also a major role in the practical training for the field staff and engineers in oil and gas production engineering and well operations for different major countries in the MENA region, USA, Canada, and Far East. Moving to SPE, Dr. Ghareeb had been the president and program and membership chairperson at the SPE Egypt section. He published and presented over 55 technical papers. Moreover, he chairs several technical sessions for local and international conferences and workshops. Finally, Dr. Ghareeb is the recipient of the 2011 and 2020 SPE Regional Technical Award in Production and Operations. So please join me in re-welcoming Dr. Ghareeb. So Doctor, thank you for the time you dedicated for delivering this course. Highly appreciated, and now hope you guys enjoyed this last session. And Dr. Ghareeb, the mic is yours.
Thank you, Mariam. Thanks, Assalamu alaikum, good morning, good afternoon, good evening. As Mariam mentioned, this is the last lecture regarding the fundamental of artificial lift technology. I will try just to give you some overview about the remaining parts of artificial lift and what are the main components, what you need to concern when you are selecting, design the system, and so on, We already talked about road lift system and electric submersible pump. Last session we talked about progressive cavity pump system. And we mentioned that as an artificial lift, this is the main common type of artificial lift, There is some few types, but it's minor used. But worldwide, this is the main common type of artificial lift using and so on. We stopped last time for the progressive cavity pumping system at these slides, We said that the progressive cavity pumping system, it's one of the main artificial lift system using for heavy crude oils. It's the best type of artificial lift systems can be used if you have heavy crude oil with sand and so on, It's represented one of the best artificial lift regarding of the total system efficiency. If you look to the total system efficiency compared to the other artificial lift, the progressive cavity pumping system or the PCP pumps is represent the highest total system efficiency. That's meaning the losses in power, in horsepower, it's much less compared to the other type of artificial lift. And we mentioned that the main component, the main part of the system are the downhole pumps, which consists of two main parts, rotor and stators, plus the drive head, plus the rod string, which is transfer the rotary motion from the surface equipment to the downhole equipment and so on. In order just to understand the design, how to design the system, what we need to consider in design, we need to understand the pump, what the factors affecting on design, because mainly I designed the system, any artificial lift system, any type of artificial lift system to produce the desired production, to produce the volume of production, what I need to produce from my wells based on the well productivity. Not only that, and to lift it to the surface with a certain wellhead pressures capable to transfer the produced fluid to my process facility or separators or whatever. Then I need two things, production as a volume and head as a lift, head, just either by feet, meters, PSI, whatever you have. Then in order to understand the PCB is working, how it's generated the pressures or the lift or the how it's produced, what's the function of the production related to the PCB. So you need just to understand the system, the geometry of the system, configuration of the system, and so on. The PCB of capital pump defined by your plans. Remember, I said that downhole pumps have two, the rotor and stators, the rotor which is rotating inside the stators. Then one of the main important parameters in the geometry, what is the rotor's diameters? What diameter of these rotors, Then the rotor diameters is the cross-section area of the rotors. But remember, these rotors, it's not a straight line just a straight bar of the steel. No, the rotor have some different shape of the steel. Then I have two diameters in the rotor. One is called minor diameter, the normal diameters of the rotors. Plunger diameter. This rotor, when you rotate around itself, have some major diameters. Major diameter is the bigger diameters. In the rotor, major diameter is a distance from crest to crest, from this crest, because if the rotor running inside the stator like this is a crest and this is a crest. This is the shape of the rotors, From here to here, it is the rotor minor diameters. And from here to here, it is the rotor major diameter. From this crest to this crest of the rotors, one is rotating around its center line, around its shaft. Then you have two diameters here for the rotors here, It is a minor diameter, the small diameter, and the major diameters, the big diameters, like this. Plus eccentricity, if you look to the rotor and stators, there's some eccentricity. If you're rotating, you have two center lines here, You have one center line, the minor diameters, and one center line, it's around the major diameter. Then between these two, there is an area, cavity area, small areas called eccentricity. Then the eccentricity is a distance between the rotor minors and major center lines. From this to this area is called the eccentricity of my rotors and so on. Plus, I have another 4 factors. What is a batch? Batch, where is the fluid that can accumulate here and here and here and here, like the stage, where is it can have the fluids. There's different batches here. There is what we call rotor batch from crest to crest. Is a rotor batch from here to here. This is what we call the rotor batch. And I have a stator batch. Stator batch, it's just this from this distance to this distance. It's 1.5 stator rotors batch, the stator batch. Then I have the pump stage. Pump stage just have 2 rotors batch like this. Then I need to understand what does it mean for all these parameters in order just to see how we can calculate production, how the pump produces the fluids, and so on, Then the pump, in order to produce the fluid, remember, I said that for all downhole pumps, regardless, ECP, sucker rods, jet pump, BCP, and so on, I have 2 types of fluids. Downhole fluids at the pump, which is a pump produces, is called pump displacement. The pump, downhole pump displacement. How much is a pump displaced fluid from below the pump to above the pump at the volume at the pump conditions? Okay, displacement of the fluid is a function of the pump geometry itself. Here for PCP, we said that the displacement of fluid equals the area, the effective flow area, plus, just the batch, the stator batch length is multiplied to the stator batch length. If I start just convert this to more smaller parameters, I say, okay, the volumetric efficiency equal eccentricity multiplied by the major diameters, the D, it's the rotor major diameters, multiplied by P by the stator batch length, the length of the stator batch. Plus I have a C, just a constant for, just to convert from the unit for this unit. Do I need this by barrel per day, per meter system, and so on, Depend on the type what we have, you can use this is just to convert. This is the eccentricity will be in millimeters or just can be in inches, and also the diameters can be millimeter or inches, and the same for the rotor batch, millimeter inch. If I use the millimeters, then I have to have, this is constant. If I use the inches system, I have to have this other constant, sorry, this constant, and vice versa. I have the other, this constant. This is a rotor batch, this is a stator patch, and this eccentricity, it's from here, and the cross section like this. This is a minor diameter, and this is a major diameter. In order just to understand this, let me give you example, what that mean and so. And remember again, this is the theoretical volumetric efficiency. Is there is any factor effect on that? Yes, there is volumetric efficiency. There is a mechanical efficiency in this. After that, all that will be also in the bump condition. At the production, at the tank condition, I need to convert this to the surface standard condition. Then the Q displacement in downhole, this one, the previous one is a displacement, is a volume displacement as a theoretical displacement, it's per day or cubic meters per day for each one RPM, for each one revolution, rotation. If you did your rotors one turn, this will be the displacement, But usually I design my system to rotate more than that in order to achieve my production. Based on production, I require then, I rotate my system and the number of rotation, it's equivalent to the production, what I need. Then the volumetric efficiency or the volumetric rates of my production, the theoretical rates is equal the theoretical bump displacement multiplied by the number of rotation, just how many turns this is PCB is turn. But remember, during the operation, there is a differential pressure across each stage. And due to that differential pressure, for sure, will be a slippage of the fluid. Part of the slippage will go back again to the previous stage because there is delta B, and this depends on the type, materials. What is what the seal line or the seal points, how much the seal rotor and stator, all that is affecting on that volumetrics or just on the what we call slippage flow rate. There is a part of the flow rate with slippage, which is just a function of my mechanical efficiency for this system. Then the slippage rate is dependent on the rotor stator fit, how the rotor and stator fit to each other. And rotor stator fit, really, it's a function of the pressure, how much pressure I need to build up, and so on. There is different factor, different parameters affect on that. Then actual production as a bump condition, actual bump displacement, the bump condition equal Q theoretical minus Q slippage. Also, there is another factor here, is volumetric. If you have some gas, some flow like this, then also there is a volumetric efficiency here. But however, just in very simple way, just the Q or bump displacement actual, the bump displaced from below the bump to above the bump, just from against the formation and push to inside the tubing is equal to the theoretical bump displacement minus the theoretical flow due to slippage and so on. Then this is an example, I give you an example in the metric system and so on, Then here what we have, I say calculate the bump displacement and theoretical flow rates. Bump displacement per RPM, and theoretical flow rates. With the bump, H eccentricity is equal 6.2 millimeters, the rotor diameter 9.2 millimeters, and the stator patch is 185 millimeters. And its operating speed 275 RPM. First of all, I need to calculate how much displacement per 1 RPM, per 1 revolution. According to this is, just this metric system, then I need to use this constant with this value, multiplied by E is eccentricity, multiplied by T is the rotor diameter 39, multiplied by, the batch. Then this is a pump displacement equal 0.256 cubic meters per day per 1 RPM. Then this can give me the, just a good configuration about how much production I need as a function of each 1 RPM. If I run the pump with 100 RPM, what will be the production? 200 RPM, what will be the production? Then at the end, the theoretical pump displacement downhole will be the displacement per 1 RPM multiplied by the revolution per minute, how many return per minute. This is 275 RPM. Then my production or theoretical production here is equal to 2.56 multiplied 275, and the total will be 70.4 cubic meters per day. This is a pump can produce downhole. If assumed, there is no gas, volumetric efficiency, and also the mechanical efficiency 100%. In order to convert these to the surface, just flow rates, I need just to consider the beta O, the formation volume factor, the shrinkage factors. Then if I divided these by the shrinkage factor, I can have the surface production rate. But for sure, this should be multiplied also by what's the mechanical efficiency. It's 80%, 85%, which is a function of the slippage, function of the rotor's condition, function of the stator condition, function of the downhole parameters, temperatures. There is different factors and so on. This just as a very simple example, to show you how to. However, there is a software, can sizing design, and with the software, all these parameters consider, not only all these parameters, all the other factors, temperature, swelling of expected swelling of my customer for the stators, what's the frictions, what the type of fluids, heavy crude oil, light crude oils, if there is a gas, if there is a lot of factors really consider. With one of the good softwares you can use in the market, it's called CFAIR. CFAIR is a good software. Usually, majority of the people worldwide is using this type of software, which can sizing your downhole equipment and surface equipment based on the production. He calculates the production using this same principle, and then after that, he can sizing the pump. He say, okay, this type of pump is much suitable for you. This is a road in order to drive the pump, because depend on the pump and pump size and conditions and the pump lanes and a lot of different factors. He can calculate the torque, how much torque required to rotate the road string in order just to produce. Based on that, how much power required to do that. Then what size of surface equipment in order to do that. The flow rates can produce the function of pump geometry, function of the pump length is a function of the revolution per minute. How many RPM the pump can be run in order to produce this for you. What about pressure? How the BCP generated pressures, and what I need to have BCP in order to have pressure. Remember, there is a certain, sizing, a certain design for speed bends, so on, and the rotor say a high percentage, majority of the conventional, there's a convention, remember, the conventional pump models, it's have a nominal lift capacity of it's around 70 psi per stator batch. For each batch of stators, I have 70 psi. That's mean for each cavity, because the stator is 50% of the cavity, you have 35 psi for each cavity. This is a cavity 35, this is a stator batch 70 psi. That means if I have more pressure, I need to increase the pump length to have more pressure than that. There is another value for the pumps can be built instead of 35 psi. Yes, because other pump manufacturing, other pump maker, and so it's can manufacturing is a pump with different, configuration of downhole, small configuration, and this just depend also the loops of the pump and how many seals, and so yes, this figure can be a little bit different, but the majority, if you start to talk, if you don't know nothing, and you start to talk about how much pressure, yes, use that value, 35 psi per cavity or 70 psi per patch, Then the differential pressure, just the pump can be built is a function of the number of stator patch multiplied by 70. For example, if I want 700 psi, then 700 psi, I need to just to see how much stator patch each stator can provide or can build for me 70 psi. Then 700 over 70 psi, then the number of stator patch I require 100 stator patch. This is just in a very simple way, But however, when you design, with the time, remember, majority of the part is a rubber. This rubber, and this is a metals, and there is a friction between rubber and the metals, and there is a high pressures here, also delta B between this and that. This could be there is a sand. This could be also, it's not exactly center downhole and so on. Then there will be some friction. Then will be some loose here, some slippage of the fluid. For that reason, when you design, not take only that factors and design. You said that I need my pump to build 700 psi, 700 psi divided by the number of stators. If it's 70 psi, then I need 100 stators. No, usually the people is taking a lot of safety factors here. And the majority of the PCB design with a target at 50 to almost 85 or 70% of its loading, Then if I say that my pumping is loaded, just need to load 70 psi, then I need just to have, 700 psi, I need to consider extra than that about more than 50% up to 75%, depend, again, downhole condition, fluid properties, what you have, stator type, rotor types, and so on. I can use that figures, 60%, 70%, 75%, 80%, the whole depth, even the whole depth, the bottom hole temperatures, and so on, Then for same pump, for same geometry of the pump, if I have the pump with the same geometry, and I need to compare these two pumps, how much pressure can it build? Remember, for similar cavity geometries, that's mean diameters of the rotors, the eccentricity, the rotor patch, and so on. When the pump, as a longer pump, will have more stage. Longer pumps, that's more stage. This is one stage, two stage, three stage. Longer pump, more stage. What's mean for you is more stage. More stage will provide higher rated lift, higher hits. When I increase the number of stage, I increase hit. Remember, before that, I have only this is about small pump. If I increase the pump, and this can be lifted or just generated for me 105 psi. If I increase the length of this pump to double or just more, whatever I increased, the pressure will increase. Instead, also to have only 105 psi, I can build up to 210 psi and so on for that. In the city hydraulics, there is another factor. Again, it's just hydraulic fluid pressures and so on. But this factor can be effect on all that, Number of continuous seals and cavities. How many number of continuous seals and cavities? Then you have more pressure and they have, because more seals, that's more pressure you have. The seal from here to here, Interference or compression fit between rotor and stator. How much is the compression fits here or interference here? It's losing, it's have two fits, too much fits, and so on. Then the slippage will be less and so on, Pump rotation speed. With the rotation speed also can some function because the slippage rates and so on. Fluid viscosity, also all these factors affect on the hydraulics of the pump and so on. Then as a design and selection, try to remember all this, when you start to use software or just to do some hand calculation. I recommend to do software for easy and so on. For the completion information, you need to have all that. What is the setting depth? Because setting depth is a function of the delta P pressure you need to build with a function with the reservoir pressures and so on, bottom hole temperatures will be a function of the depth. Wall deviation, I need to have wall deviation. What's the maximum on this wall, and especially the diameter of the tubing and so on, and in separator or sunscreen, what I have downhole, there is a tailpipe, all the downhole, and what type of downhole configuration I have, all this I need to consider while I need to design my system. Also the operating and production formation, what is the total liquid rate? Remember, total liquid rate, oil and water and so on. What is the total flow rate? Oil, liquid plus gas, and so on, water cuts, sand contains, or sand cuts, maximum minimum operating RPM. What's the maximum RPM I should run, or there is some specific minimum RPM? This is just a mechanical fact you need to consider based on your availability of your equipment or system and so on, tubing and size, head pressure. What's the well head pressure against what pressure I need to flow or bumping my system? Production gas ratio, pump intake pressure, and consequently dynamic levels. If there is a backer, no backers, what type of reservoirs, what type of inflow performance I have. Is a depletion drive or just active drive? Where is the bubble point pressures, high bubble point pressure or no? Plus the environmental concern, characteristics, what's the API of oil, what's the analysis of oils, what's the concentration of aromatics, if I have viscosity, water characteristics, as a pH and caloric salinity of the waters and so on, gas properties, a lot of factors you need to consider when you design. Whatever factors you consider, your design is, can be much better and so on. This is just, a general overview about what we need. However, as I said, hand can, it's just be easy, it can be for a very simple condition, but it's not an accuracy. Usually the PCB, you need to consider a lot of factors. You need to simulate a lot of downhole condition, a lot of downhole parameters. Depend on what? Depend on my pumps and pump configuration, manufacturing, equipment types, metallurgy of downhole equipment, well completion condition, well deviation condition, a lot of factors, The software, usually software is taking from you all what the parameter, what we have. It will ask you about a lot of parameters and simulation. And also there is an input from your side to select what parameters you need to input, because, if you input wrong parameter, for sure, you will get, could be a wrong design or just an inaccurate output results of design. However, there is a software that can help you a lot, but in order to run softwares, you need to understand what I need to put in the software. Software sometimes gives you two choices. Do I need to use this or that? You need to decide this or that based on what? Based on your background about the system, how the system running, what system, how this affects, and so on. This just as a general overview about the BCP designs and so on. At the end, like a road lift, like the PCP, the ESP, and so the pump can have some nomenclatures, usually according to the ISO, the pump nomenclatures with some parameters like this, like the first parameters, in order to know how much the pump this can be produced, how much the pump can be build the pressure or give me the pressure. Then usually the nomenclature is started with nominal capacity of this pump. How much either cubic meters, this depends on your what units you use, Either it will be cubic meter or barrel per days, nominal diameter for 100 RPM. For example, this one is tell you this is pump can produce 32 cubic meters per days for 100 RPM. If I run the pump with 200 RPM, then this pumps can produce 64 cubic meters per day, And this is the second number, it's the nominal head per meter. This pump can lifted 1,200 meters as a nominal heads, And also this is the third number is dependent on the manufacturing, And this can be different from one manufacturing to the other. And it's very important, it's elastomers code. It's very important to select this with that, because elastomer is 50% of your pump, part of the pump. Elastomer is one of the main source of downhole pump failures. Remember, elastomer is the weakest point. Elastomer, it is the main source of downhole pump failure. For an example here, this is just 32, this is what I mentioned here, is 32 1200 NH, according to this manufacturing, 32 cubic meter per day is for 100 RPM. It can lift 1,200 meters as a delta B across the pumps, and this type of elastomer is high nitrated elastomer, according to that manufacturer. If you use this is just as a barrel per day, this 200 barrel per day per 100 RPM, it can be lifted 4,100 feet, and the same, NH is the same, just type of elastomers and so on. Then pump differential pressure also rating is based on, this is all when the manufacturers give you the rate of that, is based on fresh water gradient. Because they did the test here in their plant or just as a workshop, they do the test by using the fresh water. Then you need to convert this, if you want to calculate by feet or just by feet or meters, you need just to convert this to your fluid type you have. This is just a quick about progressive cavity pump. Then we complete progressive cavity pump system. Rose pumping good type for the first artificial lift. Why? Because I mentioned majority of the worldwide use the first to and row. Let me just give to you some hints about fundamental of gas lift. What is a gas lift? How is working the gas lift? What is the main component of the gas lift? Remember, this course is a fundamental. You need to know the component of the system, because you will be not able to design. You will be not able to troubleshoot. You will not be able just, to analyzing the system if you don't know the main component. What's the component of the system? How it's working to each other, how to react to each other, and so on. Gas lift, it's one of the common also artificial lift system, but the percentage of using, it's less than the road lift, less than the PCB. Can be same like progressive cavity, in some area can be high, in some other area can be low. However, gas lift, it's one of the good artificial lift system can be used offshore if it is capable to lift my floats. Because the gas lift, as we'll see later on, it's like a flowing walls. Why I need gas lift? I need gas lift, for example, usually I simulated or design analysis. Gas lift almost is like an flowing walls. If you look to this one graph in the left side hand, this is inflow and this is outflow. If you look to that well, that's mean wells not produced. Well, in order this well to produce, outflow should be intersect with the inflow at a certain point. This type of well is not produced. Then for sure, this type of well is required artificial lift. But however, this type of well can be, in this case, flowing well in this condition because they have outflow with inflow, and this will be my production. This well, in this case, in these conditions, can produce flowing. But sometimes maybe this production is not satisfying me. It's not enough. I still have rooms to produce more flow. Then in order to shift this is outflow to a certain more point, then I need artificial lift. The gas lift can be one of the artificial lift simulated the flowing wells. Because if I use the same concept of the flow to flowing wells, I can produce the wells with the gas lift. Why? Because this is outflow depend on different factors. One of these factors, the main factor, is the gas liquid ratio. Then when the gas liquid ratio increased up to a certain limit, based on different parameters, this curve can be shifted here or there, depending on the quantity of gas. Then if I want to shift this curve a little bit here and to produce more, then I need more gas. I need more gas then I need to simulate it this way instead to be like a flowing wells, no, a flowing wells with some gas injection. It's artificially flowing wells. Then the gas lift you can consider like artificially flowing wells. Then what mean of gas lift? What is the gas lift? Then the gas lift is a form of artificial lift. In most cases, in most conditions, it's closely resemble the natural flowing pulse. It's like a flowing pulse. This is a flowing pulse. This is a casing. This is a tubing. This is a backer. Fluid comes from formation, and there is enough pressure here, bottom hole flow pressure. It's capable to lift the fluids up to the surface and overcome the pressure loss inside the tubing and the wellhead pressures here in order to reach to the flow. Then this is flowing wells. If you look at gas lift, it's almost the same completion, backer, flowing, except I just increasing the volume of gas. The volume of gas related to the liquids. Here, just increase the volume of liquid, here gas inside that. Then I just simulated like I have a flowing wells with some gas injection, artificially injected. I made this like artificially flowing wells. Then the gas lift usually use natural gas, compressed here and enter the tubing at a certain point in the bottom and just, it's mixed with the produced fluid, and just lifted this fluid. The compressed gases can be natural gas, the majority of the gas lift is used, but in some small area and some special case, it can be air, under certain precaution use. Can be mixture of gas and air, this for a special application, for a small application, for shallow wells. But however, over 95% of the wells, gas lift wells use natural gas to produce. There is 3 types of gas. If natural gas is used, it's called gas lift. If only I use air, it's called air lift. If I use a mixture of air and gas, it's named like air gas lift system. The gas lift, it's exactly the same like flowing water. Then when we start to analyzing, start to troubleshooting the gas, same concept of the flowing walls concept. It's the same, except I increase the quantity of gas with a certain precaution also. What's the advantage of gas lift? Since it is like a flowing well have plenty of advantage. Then what advantage of gas lift? Gas lift have high degree flexibility and design rate. Why? Because I can change the volume of gas. I can change the depth of gas, and I can do a lot of simulation in this case, in this condition, to have flexibility on my production. I can change my outflow curve up and down, depending on downhole condition. The gas lift is a very simple artificial lift system. There is no downhole pumps. Then all the gas lift downhole valves, it's mainly downhole valves. I can retrieve or run and just do all the downhole operation using what we call wireline retrievables, slick line. Just a very small tool of equipment I can use at the surface, can use as here, just to retrieve these valves. For that reason, as I said, the gas lift is one of the good selection artificial lift for the offshore operation because it doesn't require the rig. If I need any problem here, are very small, just like 1 ton or just maximum 2 tons equipment, I can send it to the platform. I can do operation within few hours. I can send it back again using the helicopter. Even just can move this one. It can handle sand. Condition in a very good condition because there is no moving part, and the tubing, all the tubing is open and full like this. It's allow for tubing drag. If I need to run any wireline operation, DLT operations, through tubing perforation, whatever downhole operation I need, I can run inside the tubing. It's like flowing wells. I will see later on how the side bucket mandrel is connecting to the tubing. It's taking a side of the tubing, but the inside diameter of the tube will just for your operation and so on, you know. Surface wellhead, it's just a very few. It's a Christmas tree. Plus the line, you know, going to the casing line, it's just with a gas compressed line. But the wellhead is a normal Christmas tree, like the flowing wells and so on. With one line, one compressors, you know, I can injecting gas to different wells, you know. For example, for that again, for offshore platform, I have a very small cellars, and inside this cellar I have 6 wells, 7 wells, 8 wells, 5 wells, 4 wells, and with one compressors, with the gas lift compressor, I can run all that wells only using one compressor. Then I don't need big equipment at that one. Then multi-wells can be running with a single surface equipment like a compressor. Not only that, you know, even, you know, if there is a nearby to your wells, high gas pressure wells, I can use the high gas pressure wells with some regulation for the gas pressure and gas volume, and I can produce these wells. I can connect them to the casing with a regulation here for pressures. Flow rate, I can produce these wells. Then gas well can produce me the gas lift wells and so on. Even since I don't need to big downhole equipment, slim hole completion can be good. But for sure, you know, as I mentioned before, for each artificial lift, if there is advantage, there is a limitation, there is a disadvantage. For all gas lift, the limitation, you need high pressure gas. I cannot, you know, run the gas lift without I have high pressure gas connecting to the casing and injecting the gas inside the casing. One well maybe is not economical because the compression system usually is expensive and required some more operating cost as a maintenance and so on. Fluid viscosity, it's one of the factors can affect on the gas lift processing due to slip the fluids, the gas from the viscosity due to high viscosity of the fluids and low viscosity of the gas and so on. It's sensitive to bottom hole flow pressure because it's similar like flowing wells, you know, it depends on bottom hole flow pressure. What we are doing here, you know, what all we are doing, it's reducing the average gradient of the fluid, just in order to use the same bottom hole flow pressure to lift the fluid. There is no pump here just to generate or create discharge pressure, bottom hole pressure. No, I use my same bottom hole pressure, but the only things I do, I reduce my hydrostatic head over that. Then the bottom hole flow pressure is so sensitive for that. Also the same back pressure in the surface. Because in order this bottom hole flow pressure to lift fluid to the surface, then the bottom hole flow pressure should be equal to the hydrostatic head, which is a function of the gradient, which I reduce by injecting gas, and also the wellhead pressures. And when the wellhead pressures increase, it's creating back pressure for this one. Then, gas lift as a principle of gas lift. Let me just talk you a little bit through what is the principle of gas lift. We said gas lift, it's similar like flowing wells with injecting gas. It's artificially flowing wells. What is the principle of gas lift? What is a conventional gas lift? For the conventional gas lift, if you look to this one, it's my normal completions. This is a casing. This is a tubing. This is a red one is a gas lift valve. This is a packers. This is a perforations. Usually you are injecting gas. This is a yellow arrow. You are injecting gas here for the continuous operation at the certain operating gas lift valve. When they are injecting gas here, the gas is mixed with the fluid inside the tubing. Is just reduce the fluid gradient and pushes the fluid, just since reducing, then helps the fluid to go up inside the tubing and going to the surface. The gas is injecting into the annulus. Meanwhile, the gas travels down the annulus here like this, and there is a regulator, what you call the gas lift valve, which regulates the amount of gas I need to inject inside the tubing. Then the injected gas, which mix it with the tubing, is reduce the density of the fluid inside the tubing to a point where my bottom hole flow pressures is just can lift it, this fluid to the surface. This is a very simple way how the gas lift is working. Usually one valve of the gas lift is operated. Even if you have more than one valve in the gas lift completion, we'll see later on why I have more valves. But in normal operation, only one valve is working and just injecting gas inside the tube. Then, in general configurations, like the other type of artificial lift and so, we can categorize the gas lift to two main basic type of gas lift. One is called continuous flow gas lift, and the other type called intermittent flow gas lift. What is a continuous flow gas lift? What's the intermittent flow gas lift? If you look to this shape, continuous flow, if I continuous injected in the casing, gas continuous over 24 hours, continuous gas, it's not stop, it's the word stop, that's mean it's a continuous flow gas lift. What if I injecting gas lift as a cycle? I injecting gas lift for a period of time, then I stopped for a few hours, then I gas again, I stop for a few hours, inject gas again. This is what we call intermittent gas flow. So the gas injection is not a continuous. When you use that, and what's the difference between intermittent flow gas lift and continuous gas lift? These are the general, pictures, general layout about gas lift system. As a gas lift system, usually, as I said, you need to inject the gas inside the casing. And the gas mixed with the produced fluid and going to the tubing. When the gas mixed going to the tubing, it's going to a separators. Then you separated the gas from the liquid. Part of the gas you are reused again for re-injection, and the excess gas you can go to the sales line and so on. And the oil can go from separator to the tank. This is in a very simple way, just sometimes different. You can go this to the process area and take the gas from the process area. All the gas left going on stations, and you're collecting all the oils and the gas, and take one gas going to one compressor, and compressor is distributed the gas to all the different wells based on each well requirement and so on. Then let me just give you some hint about continuous flow gas lift. In the continuous flow gas lift process, it's relatively you can have a gas with a certain high pressures continuously injecting the gas inside the casing, which is just enter to the down through the downhole valves to the tubing and mix it with the tubing. The injecting gas, I said, is joint the formation gas, because usually when you are producing the wells, you are producing formation fluids, and depend on the gas liquid ratio or gas in solution fluid property, there is a gas in solution. Then the gas what I injecting, it's mixed or just joint gas inside coming formation with the fluid, and two together consider the new gas liquid ratio. Was original liquid ratio for the gas coming from formation. The new gas liquid ratio is a gas liquid ratio at the gas lift valve and higher than that one. Then the gas lift start to this gas. It's just jointly with the gas produced gas. What happened? How the gas lift or the gas lift is a fluid. Usually the gas lift is a fluid in three different principles. Can be the three together, can be you have found two of this process, can be found one of these process, depend on different factors. As I said, fluid properties, gas in solutions, density of the fluids, depths, pressures, different factors, Mainly it's what we, at the end we conclude depend on the flow regimes. Remember, when you have two-phase flow inside the tubing, in the vertical line, you have two-phase flow. And two-phase flows, there is different flow regimes, depend on gas-liquid ratio, depends on flow properties, depend on the gas, depends on the temperature, different factors. Then the gas, when it's mixed at the valve, the injected gas with the fluid, the formation gas, with the first principle is just lifted, or just helping the gas to flow to the surface. With the first principle is reducing of fluid density. Is mixed with that, If it is a bubble flow like that, or just some mixing fluid like this, it's what we call this a gas, and this is a liquid. We have mixed flow of gas in the liquid like this. And the first principle here is reducing the fluid density, and for consequently reducing the weight of the fluid columns just which is just inside the tube. The second techniques or just second help for the gas can be help when the gas start to go up, the pressure in the gas start to be decreased. Then the small bubble of gas start to be expanded and start to be bigger bubbles of gas. Then the expansion of the injected gas commingling with the gas in solution that's push the liquid ahead further. This just work like is pushing the gas, pushing the liquid and helping that the flow to push up to the surface. Not only that, there is also displacement of liquid slug. When the gas start to go up more, this is bubble of gas start to be increased, and the flow regime start to be like a slug flow. For slug flows, on each slug of gas pushing a certain volume, like a different type of artificial lift. You can find for each well, for different well, either maybe only this case, if the volume of gas less, high liquid content, a lot of fat, low pressure, and so, or maybe you can find this case plus this case, or maybe found this case plus this case plus this case plus also some other case, and so. But in very simple principles, these are three techniques or just three principles, while this gas injection just joint the formation, gas to lift the flow to the surface by one or more of the following process. These three main processes can be, it's not can be separate or just, it's usually helping the gas or just helping the oil to be flown using the gas, injecting gas and so on. What for intermediate gas lift? How it's working, Intermediate gas lift usually used for low producers well, for low productivity well, for low permeability wells, well which cannot produce continuously, but still have a good quantity of gas. There's a good quantity of gas, but the pressure, downhole pressure, it's low. Then what we used here what we call gas assist. The gas lift assists the well to flow. Then this is this what we call it's some fluid accumulated downhole with time. Then when the fluid is accumulated downhole, due to the length of these fluid columns, the pressure here is not able to lift this to the surface. Then if I use a gas lift and I put some down just to the packer at a certain depth downhole in the well, gas lift valve and injecting gas. When I'm injecting gas, the gas come here and just push. This is just a slug of the flow here, just and lift it to the well. Then in intermediate flow, gas lift fluid is allowed to accumulate. Allowed to accumulate is that how it's, I stop the well for a period of time, then the formation start to produce inside the well, but it's not up to the surface. Produce inside the well until a certain static condition is reached, then the well is stopped to produce. Then allow this just when I have this one, this is what you call inflow cycle period inside the well. After that, I start to inject a high pressure gas. Inject high pressure gas below this slug or the column of the flow. The gas is pushed this slug to the surface and it can be produced. And as I said before, usually this is used for low permeability or low bottom hole flow pressure and so on. But however, due to this is only a slug of gas and a slug of oil and look, this efficiency usually of this type of injecting gas as intermediate, usually it's not a very high efficiency. Why? Because high percent of gas can be slipped, can be slipped down, or just a high percent of liquid can be slipped gas from the liquid. Usually the people, if they have this type of wells, it's combined this what we call intermediate gas lift with a plunger lift, which can be helped together. Then I use plunger lift with an intermediate gas lift, the efficiency of the oil can be produced and they can produce more and so on. what is a gas lift component? Is achieve all this is or just achieve this is benefit for me, or just can make this gas lift work and so on. As all type of artificial lift, they have two main parts: surface component. For the gas lift, this downhole component is a simple component. Mainly, it's have what we call valves. This is the main component, critical component in the system. It's called gas lift valve, like the pump or the pump system. In the gas lift, the valve is the heart of the system. Then I have gas lift valve. But for the other type of artificial lift, usually I use one pump. But for the gas lift, I use more than gas lift valve. For sure, it's difference in some setting and so on. But there is more than gas lift valve installed inside it. But how is this gas lift valve installed inside the tubing? Usually, the gas lift valve installed inside the tubing in this, like this, in this area, inside a device called mandrel. This is what we call the mandrel, which the gas lift valve can be placed inside it. Then the completion of my well for the gas lift, usually I run the tubing with the mandrel connected to the tubing at the depth which is designed before. I design where I need to run my gas lift valve. Then I said, okay, I need to run the first mandrel 100 feet. I need to run the second mandrel, for example, after 1,200 feet. The third mandrel, 2,000 feet, and so on. When I design like this, then my completion, when I run completion, I run the mandrel. The end of the mandrel is threaded like the tubing thread. Then threaded to the tubing, connecting to the tubing and running the well in the mandrel. Running the well in the mandrel. After that, I run the gas lift valve using the slick line and so on. Some people run from day one for the initial, but usually is run later on and so on. Depend on what's your operation, what's your company policy, and so on. What else? This is just the condition of the gas lift valve with the gas lift mandrel, and this is just the red one is the gas when injecting from the casing through the gas lift mandrel. There is small holes here. If you look here, there is a very small holes. The hole is just against the hole, same hole inside the gas lift valve. And when the gas is injecting, enter the mandrel through that holes and enter the gas lift valve from that holes. The gas lift valve is regulated and enter to the tubing and mix it with the tubing inside the fluid. Then, as a downhole equipment, I have valves. I have the mandrel in which the valve is placed, and it's working like this. I have more valve, more mandrel, depending on the well design conditions. For the surface equipment and surface condition, the first sample, I need a Christmas tree. Then I have a Christmas tree at the walls. This Christmas tree at the walls. Plus, I have some valves, valve and regulators. I have a compressors which can compress the valve. I have a controllers because I need to regulate the pressures. I need to regulate the flow rates. I need to control. I need to monitoring and so on. And this is what we call the gas compressors. The gas compressed here and enter to the annulus and mix it with the fluid inside the tubing, and the fluid produce fluid going up to Christmas tree into the fly and so on. Gas lift valve, and what is a gas lift valve and how it's working and so on. Let me just correct one point here. It's not ESP. Sorry, this is not ESP. This is gas lift wall heads. Just so that we are clear. Okay, gas lift valves. What is a gas lift valves and how the gas lift valve is working? What's the meaning of gas lift valve and why I need the gas lift valve? And the gas lift valve is used in the system. Why? To control the flow of injected gas. I need to control the injected gas. otherwise, I will be not control, and I will be not control the production process at all. Then you need to control the flow of the injected gas into the production tubing. What's the volume of gas I need to enter? Do I need just to inject 10 standard cubic feet per day, or 1,000 standard cubic feet per day, or 1,000,000 standard cubic feet per day, in order to give me a certain gas tube, and so on. Then the gas lift valve is located in the gas lift mandrel, as I mentioned before. This is a gas lift mandrel, and this is a gas lift valve, and this is just the latch which is connecting to the valve which it's using in boiling and running. This is a valve and so on. Then the gas lift valve with the gas lift mandrel is provide communication with the gas lift supply to the tubing. Operation of the gas lift valve, it's how we can determine that. Determine by preset the valve at the surface. Usually you say, okay, I need the valve to open at a certain delta B. As a delta B is the pressure inside the tubing, and what between is the difference between the pressure inside the tubing and the pressure I need to inject outside the tubing in the annulus. At what delta B the valve should be open, at what delta V the valve should be closed, because I need to open the valve at a certain pressure and so on. Then the gas lift valve, usually gas lift valve and the system have more than one valve, and there is, in general, there is two types of valves for the gas lift. Two main categories, just not only the type. If we can just divide this as a categorize, we can say have two series of gas lift valves. The first category, what we call unloading valve. Remember, I need valves, not one valve. But usually when I operate through only one valves. For that reason, I have two categories of valve. The unloading valve, the valve which is just using to unload the wells, it's open at a certain time unless the pressures reach inside the tubing to a certain pressure, and then closed again, and so on until we reach what we call the operating valve, or some people need the orifice valve. Then you have two valves, unloading valve and the orifice valve. The gas lift valve is designed to stay close. All the gas lift valve is designed to stay closed from day one, until a certain condition of pressure in the annulus reach. Then each of that valve will be closed until a certain condition of pressure at the valve is reached. The valve can be open. If this condition, like a pressure in this area, is not reached, either higher or low, the valve will be not open, and so on. Because there is a certain delta P inside the valve, there is a certain mechanism the valve can be open, and so on. When the valve is open, it permits the gas to enter inside the tubing, and so on. As an operating gas lift valve is installed to control, as I say, the point of injection. The valve are installed above the desired point of injection to unload the well. What's that mean? This is, the operating valve. If you see the operating valve, this is a loading valve, this is a loading valve, this is a loading valve, and this unloading valve. Then the valve above this operating valve is called unloading valve. Unloading valve, what mean of unloading valve? It's need only at the initial start of the gas lift, either after workover or stop the well for a long period of time, or whatever I have, when the well is not producing continuous. In the normal operation, one valve is open. Then what happens if all the wells is full with dead liquids, either reduced dead liquid fluids, or just workover fluids, killing fluids, mud, water, whatever. If I start to make unloading, just producing the well with the gas, I need a very high pressure. If I installed only one valve downhole, I need a very high pressure in order to push all that head of liquids above me. Then in this case, I need a very big compressor at the surface. Use all that operation and parameter. You install different unloading gas lift valve. While initially I start to inject the gas. When the gas is reached to the first valve is open and allow the gas to enter inside the tubing. Enter inside the tubing at these depths, then is lifting only what? Is lifting only this head of the liquid. When the gas start to mix it, lifting only the liquid. When this liquid have two-phase flow and completely is just, it's mixed with that gas, still I increase the gas pressure until I reach to the second one. But the second one, the head here, the hydrostatic head of the liquid from here to here. No, the hydrostatic head of the liquid from here to here, plus the hydrostatic head of the two-phase flow from here to here. Then the pressure here is decreased until I reach to the last operating valve. So, and the gas lift condition or gas lift operations, I say there is two main categories of the gas lift operation condition: unloading gas lift valve and operating orifice gas lift valve. Even as a gas mechanism, gas lift valve mechanism, how it's working, how it's mechanisming. Usually the gas lift is sit at the surface using a nitrogen inside the payload, inside the valve and so on. How the valve is open, how its response first to the casing pressure or response to the tubing pressure and so on. For that reason, the manufacturing start to introduce to the market two main categories of the gas lift valves. And in the basic case, in the basic condition, there is some other different valves and so on. But however, there is a gas lift valve called injection pressure operated valve. Other equipment, one of the main equipment for the gas lift, it's gas lift valves. And gas valves, it's the heart of the system. And the gas lift valve, it's usually is used to control the flow of the injection gas. How much gas I need to inject inside the tubing, The gas lift valve, and it's placed inside the mandrel like this. And the gas lift valve, when it's open, it's used to control the volume of this gas, which is just can be flow inside the tubing, depend on the pre-designed volume of gas they need to inject it in order to create a certain gas liquid ratio in order to lift this one, Then this gas is when it's placed, the gas lift valve inside the mandrel is create like a communication. If you look to these ports, is a port inside the mandrel, and the port it's against also the port inside the gas lift valve. Then when this port just communicating to each other, the gas injecting in the casing, when the gas lift valve reach to a certain delta P between casing, a pressure is open and allow a certain volume of gas to go and so on. The operation of the gas lift valve is determined by preset opening. Usually in the lab, I preset the open and close for this valve, is injecting with a certain nitrogen, gas of nitrogen, or there is a old type of gas lift valve, there is a certain spring, Inside that, I say, okay, preset for that, this gas lift valve, if the delta B across the valve, it's X PSI or X bar, the valve should be open and allow the gas from the casing to be open and enter the gas, the tubing. Main category valve to main type category depend on when I need to use a gas lift valve. What's the function of this gas lift valve? The two main categories of these gas lift valves, the first category called unloading valves, and the second one called operating valve. Operating valve, it's only one valve in the well, it's called operating valve. Usually, it's only one valve. Sometimes put some spare valve like dummy valve or just a certain type of valve, whiskey valve or something like this is called. But however, let me go simple and so on, Completion, I have more than one valve, it's called unloading valve. Plus only one valve, it's called operating valve. The gas lift valve design, all the gas lift as a principle, all the gas lift valve designed to be stay close. Stay close until what? Until a certain condition of pressure in the annulus and tubing meet. What does that mean? Usually I said the valve is preset as a surface. Then until I reach to a certain pressure across that valve as a delta P between the casing and tubing, the valve will be closed. When I reach to this certain delta P, the valve will be open. For that reason, I put a certain number of gas lift unloading valve. Why? Just in order to help me to reduce the horsepower, the pressure of gas required to start the well stopped or if the well just come after workover condition. Start to assume that this well is full with liquids, only liquids, dead liquids. If I start to produce this well and to produce with gas lift, then I need to lift all the head of these liquids. Depend on this specific gravity, assume it's water with a specific gravity 1. Then I need just to lift all that, Then in order to do that, I need pressure here, just capable to lift all this head of fluid when it's reached the gas to this one. Then the gas pressure here should be equivalent to this one. For that reason, I use what we call unloading gas lift valve. The unloading gas lift valve, it's helped me for unloading process to get the well flowing with the minimum possible wellhead gas and the gas volume at the surface. Then when I start to inject gas for dead well like this or just well full with completely liquid, when I start to inject gas here, I will see you later on some detailed slide about this. But however, I will explain in quickly that when you start to go that, the gas pushes the liquid and the liquid go inside the tubing, just because this valve will be open, the liquid push inside the tubing until I reach it to a certain pressure here, this valve will be open and the gas start to enter to this point. When gas enter to this point, mix it and until reach to the surface, reading the weight of this column from here to here, then the head here will be much less, just the total head from here will be less, the head equivalent new head of here. Then I start to inject more gas until I reach it to this second valve, and the pressure against this second valve equals the dead liquid volume head from here to here, plus the liquid already, the two-phase column of liquid or fluid from here to here, which already reduced by injecting the gas, then the pressure here will be less, and continue this operation until I reach to the last valve and so on. It's not only just the gas lift valve, it's just divided to two main categories as principle of as operation of as a function of the gas lift valve, but also as the operation principles. The manufacturing found that it's need to a different valve due to well condition and the need of the wells. However, I will not go in details of that, but I would like to just to show you what type of valves in the markets and how it's response. Usually there is two main type of gas lift valves in the market. One of them is called injection pressure operated gas lift valve, IPO. The injection pressure operated gas lift valve usually is respond to the injection gas pressure. And the other type of valve, what you call pressure operated gas lift valve, which is response to the flowing production pressure. Then one of them, it's a response to the pressure, first response to open or close, depend on the pressure on the casing. The other one, its response depends on the pressure of the flowing inside the tube. Gas lift valve. What's the function of the gas lift valve and all that one? How it can help me? First of all, as I said, it will help me in unloading the wells. It's help me unloading the wells just to reduce the volume of gas, to reduce the pressure, and not only the volume, to reduce the pressure of gas required to inject to unloading the wells and so on. What else? It's also just to provide flexibility for me for any change in the well. Just I can adjusting the volume of gas, I can adjusting the production, and depend on what? Depend on the downhole condition, the change in the problem, downhole condition, like bottom hole flow pressure, if it changes, the water cut, with time the water cut can be increased. Do I need to increase the gas volume, decrease the gas volume? Do I need to change the depths of gas injection or just what else, what the daily production I need? Do I need to increase daily production? I have problem, I need just to reduce my daily production. well drivability and so on, That's mean, the gas lift valve, it's provide me the mean of control of gas injection, the mean of control of well production. It's allow me just to optimize the well and control the well to produce as per my request. As per my request, depend on the downhole condition. I can change the parameters just to meet, to match with the downhole condition, to the well condition, change the parameters and so on. Just for unloading, let me just give me a quick view about to understand a little bit sequence of unloading and how it's unloading and so on. This well, for example, it's full of liquids, casing and tubing. It's the same liquid, and this is the gas lift valves and so on, If you start to measure what is the gradient, fluid gradient inside the casing and inside the tubing, it's the same gradient, same fluid. Then since the same fluid, to have the same gradient. And here, this is a blue one, it's tubing pressure, the pressure inside the tubing, and the red one is the pressure inside the casing. And this is static bottom hole pressures at this point. And this is my flowing bottom hole pressures, or the wellhead pressure. Sorry, this is a wellhead pressure. In this case, the well is not produced and reached to static. I need the well to produce. The well in static condition. Then I need the well to produce. Then first of all, in order the well to produce, I need to remove all the fluids. I need to remove the back pressure from around the well. Then I need just to start the gas lift process operation. Assume they have this well. This is just the pressures. This is a pressure, and this is the depths in feet, and these are pressures in PSI, and this is a static reservoir pressure. What happens if I start to inject gas? This is the injection gas, and this is a produced fluid from here. If I start to inject gas here, what happens? Here, just you here equals pressure here. Okay, this initial thanks pressure is equals the pressure here. Still I have a static reservoir pressure. I moved the fluid due to delta B because I increased the pressures here and so on. I increase the pressure like that, and the fluid is the same, just start to be pushing. I just pushing the fluid from here in order to replace this amount of fluid by gas. Then the equivalent amount of fluid here is just to the other side. If I start to just inject more gas until I reach it to the first valve. The first valve, unloading valve, is open. When the first valve will be open, the gas start to be entered in the tubing, mixed with the flow. Then you have two-phase flow here. The average gradient here, the average gradient in this will be less. It's not the average gradients like this one, because here I have gas and liquid. Here I have only liquid. And the gradient of the pressures inside the casing is different. From here to here is a gas gradient. From here to here is a liquids gradient. And this is a gas injection to compensate these liquids. And so then I continuous injecting more. When I continues to injecting more gas is here. But this valve is still sending more gas, allow more gas to enter, but I not reach to the second gas lift valve. When I reach to the second gas lift valve, more gas is reached. And just here, notice here what happened, when I start to reduce the head here, I reduce the volume. The pressure here start to be decreased. Since the pressure here against the formation start to be, what happened? The flow start to flow from the formation. Then the well start to be flowing because I reduced the pressure. I reduced the back pressure. Then the well start to be flowing according to delta B, this delta B, between flowing bottom hole pressure and static bottom hole pressure. When the second valve is open, more drop in pressure will be increased here. Then the more pressure drop will be in the bottom hole flow pressure. Then the delta B, the drawdown will be increased. Increasing drawdown, more production will be increased, and so on. You reach so on until you reach to the more valves, and the delta B will be increased. Sorry, until I reach to the, either can consider this last gas lift valve if this reach to my target, and this can be like sometimes standby if something happen, production drop, pressure dropped more, and so on. But however, this is a sequence of how to plot the gas lift valve from cease to flow well, from dead well to flowing conditions, and so on. The second part in my gas lift equipment is the gas lift mandrel. What is a gas lift mandrel? I said before, the gas lift mandrel is a place in which the valve is placed. The equipment in which you are placed your valve and so on. This is the main function of the gas lift valve, gas lift mandrel. Usually there is two types of gas lift mandrel. One of them is not used too much and used only for shallow wells and not deep wells. It's called conventional gas lift mandrel, like this one. It's a conventional gas lift mandrel. And the other side pocket gas lift mandrel, this is a standard gas lift mandrel used. What's the difference between this and the conventional one? This is a side pocket mandrel gas lift one. For the conventional gas lift mandrel, usually the valve will be outside of the mandrels. And the mandrel is like a bob joint, like a small joint of the tubing. And the valve is just installed in a certain pocket welded in outside the mandrel, and there is no access to the valve from inside the tubing. Then you need to run the valve with the mandrel from the initial point, from start up. When I start to run my completion, I installed the valve inside the mandrel, and I connect the mandrel with this connection to the tubing, and I run the oil. Then in case if any problem happen for one valve stack is not open, or I need to change the valve, need to change the setting of the valve, my downhole condition is changed and so on, then I need to pull out completely the completion to change that. For sure, is it cheap? That's operation point of view. It's not, it's not flexible, and just it's not recommended, especially for deep well. It's used for very shallow wells, just in order if they are able to compensate for the difference in the cost. If there is a small units can pull and run. But the general used gas lift mandrel, it's what we call side pocket mandrel, which is a mandrel. It's manufacturing in that shape. There's a valve run from inside the tubing using a certain techniques, which I can set or unset the valve using some, what we call the latch to the valve like this. I run a slick line, wire line operation, and just fish this fish neck, pull out the fall, change the valve, redress the valve, repair the valve, change the valve, run another valve, and run in this technique. There is a certain technique, and if you go to YouTube, you found certain technique of how to run and pull the wireline valves and so on. Gas lift design, as I said, it's flowing wells. Since it's flowing wells, then you need to have all the parameters which is just can affect on the flowing wells. You need to know all the parameters which can allow you how to select the suitable gas lift valve, how to select the depth of the gas lift valves for unloading, how to select the depth of the maximum operating gas lift valves, and so on. Then I need to know, because I will run this gas lift valve as a conventional or as side pocket mandrel. What's the tubing size? What's the sink size? What's the depth to the center of perforation? Because I will inject gas, then I need just to lift fluids. In order to lift fluid, I need to calculate the bottom hole flowing pressure. Here I work with the bottom hole flowing pressure, not the pump intake pressure. Then I need to know the depth of perforation. I need to know the fluid gravity of the API gravity. I need to know the formation gas liquid ratio. This is one of the tools can be supporting, can be help me, It's high, it's low, how much, and in order just to calculate the new gas liquid ratio to calculate just production and injection pressure and so on, Specific gravity of the injected gas and the produced gas. Do I use the same produced gas to inject or different gas? If I use different gas, what specific gravity for this one? What's the daily production? Specific gravity of water if there is a water. What's the wellhead pressure? And what expected wellhead pressure to increase or decrease, especially in the area while the wellhead pressure is changing between day and night. And sometimes some area, and especially in the desert, and the wellhead pressure can be changed between day and night, especially if you produce an oil with high aromatic, with a specific graph, if it was API 40, 42, 40 plus, and so on, there will be a paraffin, especially if you have what we call PowerPoint, the pour point of the oil. It's critical in this area, and so on. Volume of injected gas, static bottom hole pressure, productivity index. All these parameters is a very critical and need to know in order to know to sizing or just simulated your gas lift design and so on. There are several different methods really just you can use for designing gas lift and so on. One of the methods depend on, and remember the two valves, the two main valves, what I mentioned to you. Do I will use IPO valves, injection pressure valve, or I will use production injection valve and so on, production pressure valves and so on. Do I need just, I have to use a manual calculation? Usually manual calculation is not an accurate. Manual calculation there's a lot of errors will be in manual calculation. It can give you rough figures about what to have. It's some people used, it's for was not high gas oil ratio, and you will control the gas oil ratio and so on, because for the gas lift wells, you need to simulate the flow regimes, the two vertical flow. Remember I said the continuous gas flow, it depends on just in order to lift the well, depend on three processes inside the tubing, either just reduce the fluid gradient or use the slug flow or plug flow, or just use flow, what type of flow and support to help you to produce this one and so on. There is a small exercise just you can find in all the artificial lift book, and some book can help you just how to sizing this one using hand. However, I will give you some hint, small hint, in order to see that and so on. For example, assume I have a well like this, and I will need to calculate what the depths for each valve in this one. Usually, for hand calculation, you need to have a paper like this, and you draw the pressure against the depths. And also, you need to know what's the depth of the perforations and the depth of packers. Where is the packer I need to put above the perforation? Because all your injection will be above the packers, and below the packer will be only liquids. Then I need to consider all that in the design. I need to consider all that in calculating my bottom hole flow pressure, because here really depends on what will be the new bottom hole flow pressures in order to allow the well to produce. In order to know what the depths for this valve, I will just show you smallest, then the other steps you can go later on in some book you can see and so on. Remember, this is a course, it's mainly practical course, it's not a theoretical course, just not show you how to design, how to calculate. Usually you study in university, but here we try to show you some practicals and so on. Generally speaking, first of all, as a first action you need to take, first step, just you need to know what gas I have, what's the available pressures injection I have in my system, because there is a trial and error. Remember, this design, hand design calculation, there is a trial and error, because depend on surface gas, your surface equipment you have, how much is the surface equipment can used or can generated pressures and what maximum pressure can be generated and so on. But however, the first action you need just to draw the gradient line for the gas, what will be used. But why is the gradient line of the gas like this, will be like this? Yes, because these are pressures at the surface, but these are pressures at the bottom hole, at the backers and the perforations. Usually it should be at the backer when it was just above the backer and so on. But I simulated to be like this. Usually there is a gas column and the pressures increase due to the weight of the gas column. But remember, the gas also is affected by the temperatures, very high, affected by the temperature. There is different way to simulate that. You can use softwares, you can use simulation and so on. But however, in the field, usually we use what we call a rule of thumb in order to calculate that. We said that pressure at a certain depth, as a certain depth is equal pressure of gas at the surface plus what? Plus 2.3 multiply pressure of gas at the surface divided by 100 multiplied by the depth at which I need to calculate the pressure of gas divided by 1,000. This is just a rule of thumb. Huh? And when you're calculating these new pressures and you're calculating here, then you draw a line between surface pressure and these injection pressures. And I need to know what fluids I have inside my tubing. What fluid I need to unload inside the tubing. Is a water? Is a killing water from the workover or from the drilling, or just a liquids, oil, whatever I have. However, depending on the type of the fluids you have inside your tubing, you will draw from the zero line, zero depth line here, and zero pressure line. A line represent the static gradient for the fluid inside the tubing and casing, because it's the same fluid in this one. Then the second step or third step. Then I need also to calculate the gas liquid ratio, because I need just to know I will inject gas. What will be the gas liquid ratio I will inject? I will inject the gas, but there is also gas produced from the formation. Not only the gas, if there is no gas produced from the formation, then the gas liquid ratio, what I will use, is the volume of gas, what I will use as a surface. But the unloading gas liquid ratio usually is equal what? The available injection gas volume, how gas volume I have, divided by the desired production. What's the production I will produce? Okay? This if I assumed, as I said, I assumed a dead columns and no gas coming out of solution. If there is gas come out of solution, I need to consider in this case, and I need to calculate in this case, and so on. Then, after I calculate the gas liquid ratio, and based on my parameters, what is the parameters? Based on my parameters, what tubing size, what is the other side, what fluid gravity, I was water specific, if this is a water or not, how much percentage of water, how much production I need to produce. This is what will lift performance curve. The suitable vehicle lift performance curve for my in liquid ratio, what the gas liquid ratio calculate. I select the most suitable curve condition. Assume this 1,000. The calculated gas list chart after I select the suitable chart represent my condition, and I choose. I say, okay, this curve will represent my condition after I injecting the gas. The gas liquid ratio will be 400. Then I use this chart and I use this curve and I put this curve over this chart, and this one is represent the curve. What I take this one exactly, I put the two papers one over the other, and I guess use this one. You can say overlay the gas lift paper on the curve and track the curve represent your condition. This is what we design the loading gas lift. Then I have three gradients, three curves here. Gas, static, the condition after I work, after I inject the gas. Then how I select the gas lift valve, where will be the first gas lift valve, and so on. Based on that, I start to do what? Here, you usually use triangles and just triangle and rulers you can use, and draw a parallel line to the static gradient. This is a static gradient, my static gradient. Then I said I have three curves. This one, and also this one, and this one. I draw the parallel line from my static curve until from the point, the wellhead pressure point. This is a wellhead pressure point, which I draw my curve as a wellhead pressure point. Then I draw the line from the wellhead pressure line parallel to that line, the static line, until intersect with what? With the pressure of the gas line at this point. Until intersect with the gas at that point. For the operation principle and the valve and the condition of the valves, and in order the valve to be open and closed, usually, locate the point on the static gradient where there is at least 30 psi of differential pressure between what? Between the casing and tubing, because you need to have delta P between the casing and tubing in order the valve to be open. However, after you do that line, and this is just intersect this with the gas pressure line, you go with a difference about, if you have this just focusing, zooming in that, you have a difference out. This was about 30 psi in this line. You go out about back, you can start to go back 30 psi, and you can start to draw horizontal line in this one. And intersection horizontal line with this axis represent for you what? Represent the first gas depths of the first gas lift valve. What is second gas lift valve? The first gas lift valve, usually since I'm injecting gas in the gas lift valve, it's sensitive to gas and will open with delta P of gas, especially for the first type, the valve which is sensitive or operated by the injection gas and so on. I need to know the temperature at that depth, because there is a temperature gradient. You need to draw after that temperature gradient, because you need to know to do some correlation, some calculations, some correlations about, corrections about the gas and the gas lift valve and the pressure open of the valve will be open and, then determine the valve temperature as gas lift depth 1 on in the top table of your table. The temperature can be calculated from the temperature gradient and so on. However, you can do the second valve, third valve until to reach to the bottom using the same technique. But if you look to there is a lot of softwares in the market can do very easy that for you if you enter with a good input data and so on, because hand calculations sometimes is misleading, especially if you are not use exactly two-phase flow correlation. Because remember, this curve is depend on what? Depend on the flow correlations, just that all the gas will be mixed homogeneous with the float. But in reality, this is not happen. When you have two-phase flow inside the tubing and the vial, will be different flow regimes. You have bubble flow, slug flow, mist flow, you have annular flow, all type of flow you have. At what flow regime you have inside the tubing. This curve will be completely changed. Then the depths of the valves will be slightly changed from what you designed. However, this one of output of the software you can use to sizing to your gas lift system or design gas lift system. One of the important points while operation and so on, someone can be asking, since the gas lift is good, why, and I can inject more gas to produce more liquid and so on. No. There is an optimum volume of gas to be injected to reach to your desired production. Other than that, if you start to inject low or high, maybe you lose production. High, you lose production because if you produce more gas, sometimes the gas will be slipped and we lift the floats behind because the velocity will be high and so on. Then after a certain volume, this is just a general relationship between production rate for a certain wells and the injection gas rates is still okay. When you start to increase the injection gas rate, your production rate will be increased until a certain area, what we call unstable gas injection in this area, because there is no stable gas injection, can be fluctuated and so on. There will be increase until you reach to optimum gas rate. After that, the optimum gas rates, whatever you inject of gas, you will not gain more production. Sometimes the production will be decreased and so on. There is another main important just for gas lift. The valve unloading valve is different than the orifice or operating valve. And I put this just for you in order to see what's the difference between the valves and how can be the gas lift valve. And there is different type, even for the orifice gas lift valve, different type, different size, and different material and so on. This is just a quick overview about gas lift. Let me just also give to you some more information, basic information about the jet pumping system. Jet pumping system, it's one of the artificial lift system. It's called what we call a dynamic displacement artificial lift system. Its general description of this one, it's a hydraulic pumping artificial lift system. Because there is different type of hydraulic pumping system. It's what we call jet pump and piston. But however, the jet pump is one of the main common artificial lift as hydraulic is used. The hydraulic artificial lift system is operated by what? Operated depend on pumping, instead of pumping gas, remember? For gas lift, we are compressed gas to the tubing, to the casing in order to produce. Here we are pumped fluids to the well in order to produce the fluid. You are pumped either from tubing and producing from the casing, or pumped from the casing and produce from the casing, depending on the condition. This is a downhole pumps configuration. It's only hydraulics pump with a very different small tubes inside the pump, different configurations, and so on. I injected fluid, which is called power fluid, and the injection pressure is called power pressures, and so on, and so on. Then for jet pump, it is the hydraulic dynamic displacement artificial lift pumping system. Advantage of the pump, there is no moving parts. If we see this pump here, there is no moving parts in the pump. Also, you know, it can produce high volume. When I start to looking to well producing high volume, one of my first choice is the jet pump, like ESP, like gas lift. It's free pump styles. I can pull and pump. I can retrieve the pump from the well without any intervention inside the well, either wireline or operation or so. By changing the direction of the injection, I can just retrieve the pump out the well and so. Since there is no moving parts, only the moving here is hydraulic, is a fluid. Then the well is excellent for deviated wells. I can use one surface equipment to feed different wells and so on. The limitation of this well production is rate is relative to the bottom hole pressure. Since I inject fluid, yes, I inject fluid, but I inject fluid with a certain pressures, with a high pressure. Then sometimes this high pressure, in order to lift that fluid, is creating a little bit back pressure. I reach to a certain limit. More than that, I cannot reduce the bottom hole pressure, and so on. It's required a specific bottom hole configuration in order to set the pump. However, the majority of the pump can be set inside one of the well completion tools called sliding sleeve. But if I need more production, then I need special bottom hole assemblies. One of also the problem, just or limitation or just disadvantage, like the gas lift, it's low horsepower efficiency, low total system efficiency. Then gas lift, hydraulic lift, it is the lowest total system efficiency artificial lift system. It's high pressure surface produce it and inject fluid with high pressure. This high pressure is creating some safety hazard at the surface and so on. But jet pump completion. What type of completion? Since jet pump is only depend on the completion and how it's running and so on. What type of completion, how I include, how I produce, and so on, you know. With a jet pump application, I need 3 conduit. What mean of 3 conduit? Then I need 3 like conduit pipes in order to produce pipe wells. Why I need 3 conduit that one? First of all, I need a conduit for the fluid, reservoir fluid, because there is a packers, and below the packers there is a fluid, and I need to separate it, isolate it, the produced fluid from the injection fluid and from the produced fluid. Then this area inside the casing is what you call the first conduit for you. What's the second one? I need a conduit for the injected fluid, injected bar fluid, either inside the tubing for the standard or inside the casing for the reverse. Then this is the second one. What's the third? I need my third conduit for production. Then I need for fluid from reservoir to the tubing intake or pump intake, but for the bar fluid, I need conduit for fluid, and I need production. There are 3 typical completion type for well equipped with well completion. What's the typical completion for jet pump in order to achieve all that? First of all, this is a standard completion, tubing, I use tubing, casing, backers, and this is a pump condition. This is a main common type of completion, or sometimes I use 2 tubing connecting here just at the pump, one for power fluid, one for produced fluid, and usually use that if you have a problem with your casing. Sometimes here I use a casing, either I produce or inject through the casing. But if I have a problem with the casing leak, casing corroded, I cannot use the casing, then I need to run with this type of compression. The same for this one if I have a problem with the casing, or if I need just to monitoring my bottom hole pressures, because here I cannot monitoring my bottom hole pressure using fluid level condition and so on. Or for low pressure bottom hole pressure, low pressure wells, you know, in this case, you know, I can create low pressures here without effect in the formation at the back pressure and so on. As a main component for the jet pump, we have self-pumping should be have high pressures, positive displacement or just centrifugal pump, a high pressure pump. However, I need pump to generate high pressure, high volume flow rates. Then I need the vessels to isolate liquid, solids. If I use a produce fluids and gas and so on, you know. Plus, downhole. I have downhole pumps, and the downhole pumps have 3 main components: nozzle, throats, and diffusers. What is a typical downhole jet pump? For standard downhole jet pump configurations and looks like. We said this is my well completion. This is a tubing, this is a casing, this is a packers, this is a downhole pumps. If you look from inside the downholes, this is actual downhole pumps, real downhole pumps have 3 main components, I say. Usually downhole pumps have 3 main components: nozzle, throats, and diffusers. Here is a nozzle, very small area, and these are diffusers. These are 3 main areas where the pump should be used in order to produce a fluid, in order to generate the pressure formation. Other parts is just, you know, the part to complete the pump for power flow pass, for production flow pass, connections, fishnet connections, and so on. For standard pump or just reverse pump, 2 types of jet pump operations you found in the oil and gas industry. What the mean of 2 pump operations and what's the difference with 2 pump? One type of operation, one type of pump called standard circulation pump. The other pump called reverse circulation pump. What's the difference between standard circulation and reverse circulation pump? For standard circulation pump, the power fluid is just it's injected inside the tubing. Sorry, just a minute. And for reverse circulation pump, the power fluids is injected inside the casing, and the produced fluids is produced from the tubing. Then I have two pumps, two open for the pumps. Then I have two standard pumps, or just two different pumps. One what we call standard circulation pump, the other one is called reverse circulation pump. Standard circulation pump, the power fluid is injected from the tubing, and the produced fluid produced from the casing. And for reverse circulation, vice versa. The power fluid injected from the tubing, from the casing, the produced fluid will go out from the tubing. This is a wellhead configuration of the tubing of the jet pump. Usually, it's a very simple. You have Christmas tree, plus sometimes you have a catchers in case you need to catch the pump by reverse circulation. You have different valves. Usually a set of valves used for production and injection operation, and the other set of valves are used if I want to reverse back the pump from the well. So it looks like this is a well-lit Christmas tree, the pump catchers, and this is just the controllers on, and these are pump stations, and this is another layout of the pump station, how it looks like, and how it's work, and so on, you know. How the jet pumps work? Increasing the pressures. It's hydraulics, and since it's hydraulic, then the pump should be increase the pressure. What's the principle of the pump in increasing the pressure? The jet pump, when the power travel, here is a nozzle, is one, a very small area, few millimeters. It's a nozzle, and have a high output pressure, with a high pressure, with a high rate, assumed 2,000 barrel per day, with a pressure when it reaches here, it's around 3,000 psi. It's all its pass from an area, it's around 5-6 millimeters. No. To the Venturi effect, the pressure watts will convert it to speed. Then the pressure will decrease and increase the speed of flow. This area called throat then the flow coming from the formation in this area will found this area with a very low pressure. It will move in that area. Usually the flow is moved to the low pressure area, and the fluid will move to this area, while this power flow also is moving with high velocity, low pressure in the same area, what we call throat of the jet pump. At the throats of the jet pump, what will happen? The velocity will start to decrease with the distance. It will be away from this one. When the velocity start to be decreased, what happens? The pressure will be increased. Pressure here will already start to be mixed together in the diffuser. Diffuser, it's start to be, the areas will be bigger and bigger. Then the two fluids start to mix here. When the fluids start to be mixed here, the speed start to be decreased, the pressure be increased again. For sure, in this area will be a delta P between this pressure and this pressure, all this pressure loss. For that reason, we said that this is one of the reasons the jet pump have low efficiency, high pressure loss, high power loss inside the pump, and so on. However, depend on the ratio between nozzle and throats, nozzle and diffusers, and all this area with the ratio, there is different type of pump. It will depend on this ratio, what we call A ratio, C ratio, E ratio. Each manufacturer got different configuration. Depends on the ratio. Look to the ratio here between this area and this area, this area and this area, this area and this area. Depends on the ratio, you can have, different pump capabilities as a pressure and flow rates and so on. This is just about the jet pump. What about the last artificial lift? It is a plunger lift. The plunger lift is one of artificial lift. Really, it's common use to work with gas wells, especially with gas wells or very high gas liquid ratio wells and very low production oil wells. And what is a plunger lift? This is just a shape configuration layout of the plunger lift. Plunger lift is an artificial lift system. It's not used any type of pumps, not used any outlet source of power. It's artificial lift usually used for low production well, high gas ratio wells. This well should be low production and high gas ratio. It is used what? It is used the well own energy, the well gas just to lift accumulated fluid of liquid from time to times, just like a cycling of this liquid. It's trouble free. Like if someone work with in the field with what we call swabbing, it's like an automatic swabbing. The plunger used what we call the plunger technique, plunger lift system, used a free traveling piston, just to lift the fluid, which is also should be fit inside the tubing, because the plunger outside the diameter should be almost a little bit less than the tubing inside the diameters. It's make like a mechanical seal between the fluid inside the plunger and the case and the gas inside the casing. Advantage for this one, required no power to run this, just only use the well pressures, the well gas, energy to produce the well. Then it's no outside energy, it's use the energy the well energy to lift the well. It's easy to maintenance, no bumps, nothing, just downhole, no complicated configuration downhole. It's very easy to maintain and so on. It can be also used to keep the well clean. The plungers going up and down, always keeping the tubing cleaning from paraffin, from scales, what problem to have, It's excellent for small field or one is, if you have a very small field or even one wells, I can move from one well to the other wells. It's a very good for high gas ratio wells and so on, It's a very cheap artificial lift system. It's the cheapest artificial lift system and so on. But remember, since there is no outside source or no outside power to use these wells, then there should be a certain criteria to use this well in order to work. This type of artificial lift, in order to work, there are certain criteria should be achieved in this case. What criteria is this one? The liquid ratio should be not less. Sometimes some people prefer to be higher. Not less than 300 standard cubic feet per each 1,000 feet of the well. What does that mean? For example, if I have a well produced from 1,000 feet, then the gas liquid ratio should be not less than 300. If I have a well produced from 2,000 feet, then the gas liquid ratio should not less than 300 multiplied 2 should be 6,000 feet. 3,000 feet wells, then the gas liquid ratio should be minimum, at the minimum, it should be 300 multiplied by 3 should be 900 standard cubic feet. This for open casing, for open annulus. That's what mean of open annulus. That means there is no backer downhole. Just no backer downhole, then I use a gas to be stored in the casing, and this can be required low gas ratio. But if there is a backers inside the well, then I need a very high gas liquid ratio for plunger lift to work. For that reason, you will not find not many plunger lift working for wells equipped with a back. In this case, you require at least minimum 2,000 standard cubic feet for each 1,000 feet of depth of the well. Must have no obstruction in the tubing, because the plunger going up and down from the bottom to the surface of the wells. Then inside the tubing should be no obstruction, no collapse, nothing obstruction inside the well for the plunger to move up and down. Must have a good built-up pressures, just because to allow the fluid to accumulate it inside the well. In most cases, the plunger lift usually is not used for well produce more than 200 barrels per day. Are used for well produce 200, 150, 25 barrels per day, 6 barrels per day, and so on. Since the plunger lift, it's used use a well gas condition. It's usually required a continuous optimization for this well. For that reason, surveillance and optimization change parameters, using the weir, using that is required continuous to have this one. Application, yes, it can be used for different type of well, mainly gas wells with liquid loading, mainly for the watering gas wells, unloading naturally flowing wells, shut-in, but should be have a very high gas ratio wells, just can be used combination with what? Combinations with intermediate gas lift to reduce the volume of gas I use for intermediate gas. This can be used to clean the wells, is have some paraffin, some scales, and so on. What's a component? You have two main components, surface and downhole. Downhole component mainly have three main components: bumper spring and landing. Spring and landing is fixed downhole. Plunger is moving inside the tubing from the bottom to the top. Plus, I have the wellhead component, which is lubricators, control valve, motor control valve, sensors, and also solar panels, all these components. Let me just go a little bit one by one and show you the picture of some of these and how it looks like, and so on. Plunger lift component, as I said, before, we have the plunger. It's a plunger, which is a moving part, the heart of the system. It's considered like a pig, which just move the fluid, push the fluid from inside the tubing to the surface. It's a device provide keel for the fluids inside the tubing to deliver the fluid to the surface. There's different type of plungers. Depends on the well condition, depends on downhole parameter, downhole pressures, gas liquid ratio, pressure build-up, and so on. There is different type of plungers and so on. And also there is a bumper springs installed in the bottom of the well. And the bumper spring used just like a shock absorber for the plunger, because the plunger is traveling, to the surface. And what's pushing the plunger is the gas. Below the plunger is pushing the plunger to the surface. But the plunger is back to the well by under its own weights, and it's back to the well using the gravity under its own weights. And due to the velocity and the impact of the plunger over that, you need to have something like shock absorber, to absorb all the force of the plunger when it's hitting the bottom hole condition. Also, there is different configuration of the bumper spring and so on. Plus the landing, where is the bumper spring will be stopped. And how can I isolate it, just from inside the tubing and from below the plunger and above the plunger. There is also different type of what we call landing tools and so on. The surface equipment, here I have a lubricators. It's one of the main important part for the plunger lift. Like the plunger is a lubricator. It's the topmost part of the plunger lift assembly. There's different configuration, different types of the plungers. Either can be threaded bottom or can be flanged bottom. connections, can be in this connection or that connection, how it's connecting for the flow, it's connecting all that, where is the sensor is connecting, which is can catch the plunger inside it if the plunger, or even if I need to change the plunger and so on. What else? I have sensor just to sense the plunger when it's reached to the surface. When the plunger is reached to the surface, the sensor signals these valves in order to open or close, when this sensor can be changing the direction of the flow and so on, This is what we call the motor control valve, which can be open and closed. The motor control valve just depend or pressure activated design. He will sense by that casing and wellhead pressures, and based on these two pressures, he can sense the difference, and he can be open or closed in order to allow the plunger to run or just to keep at the surface. Plus, I have what we call the well controllers in order to control all these systems. And the well controllers is operated by what is operated by a small solar panel. There is no outsourced power unless this small solar panel is used. How the plunger lift is operated? There is 3 stages of operation for the plunger lift. As I said, one stage and other after flow stage. The operations, what does that mean? That off stage, that's mean when the well in this case is turned off, closed from here, no floats, there is no flow just for the wells going on, and the plunger start to go down. You are close the well from here, plunger fall down until it's reached to the bottom of the tubing here, at the top of the tubing. Then when the plunger reaches to the top of the tubing, there is a float inside here already, The plunger is full inside the tubing. What will happen here? The well is just closed, and just in this case, the well is closed, and all this will be afloat up to a certain limit, and here there is a gas. What will happen for the on flow? On flow, the well is producing and plunger is traveling. When the gas here will have enough pressure to lift the plunger, where is the plunger to lift the fluid, enough pressure to lift the plunger with the fluid over the plunger. This is amount of fluid which is just built up and accumulated inside the well during the off period. And in the on period, the plunger when start to be open, what will happen? The plunger is just traveling with this, is carrying this amount of fluid up to the surface until the plunger reaches to the surface. When the plunger reaches to the surface, he will catch the plunger and will keep the plunger in the surface if the well able to flow for some time. What we call this after flow. After flow, that means the plunger reaches to the surface after it cleans the well from the back pressure due to this column of the fluid, and the well start to be produced. The well start to be produced and will be flown until the well start to be, cease to flow, because with the time, this amount of fluid will start to drop back due to low velocity of the fluid and so on. When it start to drop back, this fluid, then the well start to give a signals to the plunger, and the plunger start to go down again, and the period start to be just, repeated off stage, on stage, and after flow stage. This is just a general overview about the plunger lift. Let me just give me some hint, one slide, about what the futures for artificial lift. Currently, a lot of people use a combination of artificial lift. It's combine different type of artificial lift to get maximizing efficiency of the lifting techniques. Some people use gas lift with ESP. Some people use plunger lift with gas lift. Some people even use rod lift with ESP, and so on. There is a different combination, plunger lift with a gas lift, and so on. This in order to increase efficiency on the power. One of the very important just summary, I like to remind you about artificial lift selection and design. You need to know what the challenge you will face in selecting your artificial lift. What's the challenge you will face in operating your artificial lift? Usually, difficult float is one of the main important challenges. Difficult float, high viscosity, high water cut, high gas ratio, fluid with high sand content, a combination of all of that. This is a difficult fluid, corrosive fluids, very high corrosion, H2S, CO2, all this is challenge. What type of artificial lift I need to select? What type of artificial lift I need to select to have a very long running life? I need to have a very high operating times for this one, very low operating cost, and so on. What the well conditions? Where is the well working locations? Offshore, onshore? What production? Is the production stable production, high production, low production? What's the whole consideration? Deviated wells, what's the dugleg severity, horizontal wells, and so on. What type of reservoirs, and conventional reservoir, unconventional, depletion drive, water drives, gas reservoir, oil reservoir. At the end, all that will conclude to economics. I need to produce a well for economics, not I need to produce a well for production. Production is economics. Artificial lift is an economics, and so on. Then, what you need from your artificial lift, remember this four very well. You need from your artificial lift to maximize your output of artificial lift, and order to maximize your output from your artificial lift, minimum, you need four things. You need to ensure the equipment production and producing in the optimum condition. You need to have a minimum possible equipment downtime. If you run continuous equipment, no downtime due to failure, no downtime due to failures. Also, you need to minimize the intervention frequency. If they were running without any workover, without any servicing, this will be great and well. You need to minimize as much as you can for this, for economics and for safety as point of view. Try from time to time to introduce the innovative technology, not to depend only in the old technology, and you can face a lot of problem and maybe not able. Currently, and in the market, there is a new technology can overcome all the problem what you can expect it and what you have. Then, at the end, optimization. Always try to optimize your condition, your well, and so on. And what optimization can be meaning for you or just needed for you? You need to manage production of hydrocarbon. Things change over time. Remember, the well conditions, the float conditions, the parameters, everything is a change with time, change with production. Then you need from time to time, you always optimize your wells. You need to implement the best lift technology. And this can be from starting point. As a good start for you, what's the best technology of artificial lift you need to implement? Surveillance and measurements, what happened? This will tell you what happened. Continuous surveillance, measurement downhole, surface, and so will tell you always what's happened, what's going on. And analysis also will allow you from the data and measurement, from a data collection, we're going to do analysis, what's going on, what's happened, and what expected can be happen for this well, what's the design of solution, how can I improve my performance, and so on, how to manage my assets, and so on, At the end, my KPIs and the feedback. I need to monitoring my KPI, reporting my KPI, and the feedback, and so on. Then observation and automation, remote monitoring, continuous monitoring, continuous analysis, teamwork, innovation, technology, all that will help you to improve your artificial lift technology and output of artificial lift technology, and so on. This just, conclude for what we are talking about as a general artificial lift. This is the main type of artificial lift in the market. This course is fundamental principles. Inshallah, we plan for another courses like a design, operation, troubleshooting, and so on, for more advanced courses. But the more advanced courses, you must pass this course in order to attend the more advanced course. And When you select your artificial lift, use some guides in front of you. When you're screening artificial lift, use some guides in front of you, and so on. I would like to thank all of you, and sorry if we just will be a little bit long today in these lectures. Thank you, Anson.
Thank you, Doctor, for this informative. Yes, thank you, Doctor, for this informative session. Now we'll begin with the questions. So the first question is that what is the relation between the productivity index and the operating orifice valve, if there is any?
Yes, there is for sure there is a relation. Productivity index, it is a reservoir parameters. Orifice size is equipment for artificial lift. I will selecting the orifice size and the orifice configurations in order to produce what the reservoirs can produce and can give to me. Productivity index is reflect to the production. Productivity index, it can be changed with change some parameters, like changing reservoirs conditions and reservoir static pressure and just some skein effect, some parameters, and so on. Then the orifice size in this case should be changed depending on how much reservoir will produce and will give to me, it's allowed to me, and so on. Because in the orifice will allow me just, to pass, allow me to help me to support bottom hole flow pressure. And the bottom hole flow pressure is a factor productivity index. Productivity index equal flow rate equal delta P. And delta P is a factor of that. This is just as a general, As one of the main factors when we design a system, I need to have not only the productivity index, because productivity index is a straight line. I need to know exactly what is my well and flow performance. Okay, no?
Yes, thank you, Doctor. Now the second question is that which is more efficient, the production pressure operating gas lift valve or the injection pressure operated gas lift valve?
Both of them is more efficient, depend on the well condition. When I need to that, each one is each one have a certain type of applications. Some people said the pressure valves, it will be it's more efficient than production valve, and it's used more in the markets and so. But however, at the end I cannot say who's more efficient. Because sometimes maybe one of them I cannot use at all. Maybe one of them is just it's showing 50% efficiency than the other. I cannot blame the other type of valve, but I blame the condition which will be the best application for that valves. Usually it's not say you have these two valves, try to select one of them. No, have these two valves and these two valves work. This valve work in this condition. This valve work best in this condition. This valve has advantage in this condition and disadvantage in this condition, and so on.
Yes, okay. Great. Now the last question is that would the electrical submersible pump be economical to be used if we have a well with low production?
Usually we can say no. Well, with low production, there is a system to use that, because low production also depends on how low. Someone, if you ask me low production, I can say 50 barrel per day, or just 100 barrel per day, or in some area, like in Aramco, we say 500 barrel per day is low production. In some other area, like in Egypt, I say it's 500 barrel per day is high production. However, for low production, according to the publications, according to the researches, according to all the statistics, they said, if the beam pumping system, the reciprocating pumping system, can produce your wells, go to this type of artificial lift system because will be more economical. More economical, why? Because the majority of the capital investment in the surface and downhole equipment is only pumps, downhole pumps and rods. and easy to manage all that, and easy to repair and change in the fields, easy to change in the field. But however, I don't like just to give this as a disadvantage for ECP. Sometimes ECP will be more economical for low production. For example, if I use offshore, if you inform me that's low production offshore wells, in this case I say yes, beam pumping cannot be used, but ESP cable deployed ESP, for example, yes, can be more economical in this than rod lift in this. It's relative. At the end, the screening of selecting the artificial lift depends on different area. If you inform me low productions in the area with the majority of the well running with ESP, and there is a workover rigs, and there is a rigs can be used, that's maybe I can say yes. In this case, maybe the ESP is economical. But if you inform me in a remote area and far well, maybe it's even not low production, maybe medium production, maybe the ESP is not economical, because ESP require the workover rig in order to retrieve and replace the downhole equipment. And the other type of artificial lift, maybe jet pump, would be more economical than these two types of artificial lift, because it's not required a surface equipment, not required a surface rig. You can retrieve the pump or run the pump. You can run the pump by drop from the surface. You can retrieve the pump by reverse circulation. It's relative, the economics here. You need to have all the conditions in front of you. Let's see, okay?
Yes, okay, great. So thank you, Doctor, for your time and effort. We were pleasure to have you, and we're looking forward to have you also in future courses. Now, as a reminder, the final exam for this course is held on Saturday, 10 a.m. Egypt time and 7 p.m. Egypt time. However, you're only required to attend only one exam. Now, best of luck and have a nice day, and see you in future webinars.